Indian Railways moves tens of millions of people every single day. When you pack hundreds of passengers into a speeding metal tube, a single unchecked spark in a confined space creates a scenario that can spiral in a matter of seconds. Modern rail defense relies on a sequence of interlocking layers, functioning as a responsive, escalating ecosystem of detection and suppression. To understand how this interactive shield actually functions, we have to look past the individual tools and see the logic of the escalation itself. That threat has been part of rail transit since the beginning. Early steam locomotives were driven by coal and immense heat, requiring constant vigilance from the crew to keep the fire where it belonged. Back then, if a fire broke out on the tracks, the response was reactive. The train had to stop and wait for a local fire brigade, like this vintage Nizam State No. 1 fire engine, to arrive from the outside. Today, rail safety operates on a proactive timeline, triggering automatic countermeasures before a human operator is even aware of the danger. The first line of defense looks for microscopic anomalies. Long before you smell smoke, specialized sensors are already pulling air inward to sample the environment. This cross-section reveals the internal mechanics of a modern smoke detector. When a particle enters the sensor chamber and interacts a light beam, it sends an electrical signal straight to a printed circuit board, which then triggers the flashing LED indicator on the ceiling. Smoke detectors are backed up by thermal sensors that quickly track rapid temperature spikes, and ultraviolet and infrared sensors that actively look for the specific light signatures of a flame. Together, they instantly trigger the main fire alarm panel, activating hooters and strobe lights across the station. By removing the delay of human reporting, this automated sensory web secures the most valuable resource in any fire scenario: seconds. Those sensors also bridge the gap to physical action. In confined compartments, automatic modular fire extinguishers closely monitor the room temperature. If it hits a specific threshold, the heat-sensitive glass bulb violently shatters, releasing a downward burst of extinguishing agent. In this internal cross-section, the manual extinguisher acts as the immediate heavy hitter. Pressing the operating lever opens the valve assembly. Internal pressure instantly forces the extinguishing agent up from the cylinder's bottom, through the siphon tube, and out the discharge nozzle. Passengers and staff also have access to low-tech, immediate alternatives. Stations provide bright red fire buckets, filled with heavy sand or water, and thick, resistant fire blankets, to quickly smother small flare-ups. These first-strike tools exist for one specific reason: to smother a localized threat in its infancy, before it spreads and compromises the carriage structure. But if a localized fire outgrows those initial capabilities, that is exactly when the railway station's heavy suppression infrastructure suddenly kicks in. Here, the primary fire pump draws water through a suction pipe. A rapidly rotating impeller spins it outward into the hydrant line. This high-pressure water travels through airtight couplings into a fire hose, protected by a woven jacket and rubber lining as pressure builds. By tapping into this massive water supply, the heavy infrastructure effectively turns a passive railway platform into an active, high-pressure suppression weapon. When a fire fully escalates, the surrounding environment quickly becomes toxic and structurally unstable, making it impossible to breathe or navigate with advanced survival gear. This detailed illustration breaks down the self-contained breathing apparatus, commonly known as the SCBA. It features three main components: a pressurized air cylinder on the harness, an airflow regulating demand valve, and a sealed face mask keeping toxic smoke out. If doors are warped by heat or debris blocks an exit, responders deploy heavy rescue equipment. Tools like hydraulic cutters, powerful hydraulic spreaders, and the traditional steel fireman's axe are used to pry open jammed infrastructure. This final layer of hardware exists solely to protect the rescue operatives entering a deadly environment to retrieve trapped passengers. To actually operationalize this technological arsenal, Indian Railways relies on the essential tacticians on the ground, the Railway Protection Force. The RPF operates under a strict prevention mandate long before a spark even happens. They inspect tamper seals on extinguishers, verify gauges are in the green, and ensure exits remain completely unobstructed. If a fire breaks out, their tactical protocol activates. They immediately raise the alarm, deploy the exact class of extinguisher needed for that specific hazard, and execute an organized crowd evacuation away from the hazard zone. Once the flames are out, the work shifts to recovery. The RPF secures the incident site, preserves physical evidence for investigation, and rapidly replaces spent cylinders to reset the defensive line. The anatomy of railway fire suppression is built on a complex, escalating timeline of technology, but ultimately it is the vigilance, discipline, and training of the RPF that transforms these tools into a functional defensive line.